Okay, we're live, Marta, yeah?
Mm-hmm.
All right, great. Good evening, everyone. Thank you very much for being here. It's really appreciated. Session 5 of 6, so we're getting there. Been quite an experience so far. Marta, just turn that back up a little bit from where the main volume from where it was. Yeah, that's better.
Yep.
A couple of very quick things. We're going to get straight into it, basically. You've seen on the screen that we've had up a few moments ago that we'd really like you to communicate with the show. So hashtag TELCPD. We've actually changed that from the Biomechanics one. That you can put on Twitter, and we'll pick that up on Twitter with you, and we'll answer it here in the show. You can obviously comment into the YouTube chat as well. It will ask you to sign into Google, and it sort of says something slightly concerning, which is create your own channel. Don't worry, you don't need to make any videos or anything like that. It's just so that you can contribute to chats and things like that. So feel free to do that. And we also had the phone number up on the screen. Marta, can you actually push that back up?
Sure.
Is that possible for you to do that?
Yep.
And what we're going to do there is, the idea of this is that you can text that number, and we'll receive your question that way. But also, we might call you back and get you up on get your audio on the session as well, so you can talk to us directly. So if someone's brave enough to do that, we've only had one or two occasions where people have been brave enough to do that in the past. So go on, get stuck in and do that with us. That would be great. And also, as I should have said, please do subscribe to the YouTube channel if you're able to. It really is. It really is good for us if you can do that. It helps us a great deal. So do that. That would be brilliant. Okay, so I think we're ready. We're going to go into airflow, Marta. Marta briefly asked me before. I should have introduced you. Marta's with us this evening. Marta.
Hello.
Marta, do you have a nation this week? Are you Spanish or Catalan this week? Can I just ask?
I don't know. It's complicated. Officially, I'm still Spanish, so
Okay, we'll keep an eye on that.
Yeah.
And we're doing airflow tonight, and Marta asked me a moment ago, airflow, has that got anything to do with Hoovers? So let's see if it does. So we're going to get straight onto the show, Marta. If you can push us onto the Canvas stream. And then we'll go from there. Thank you.
Okay.
You already know the classroom model which we use. You're very welcome to adopt it. You're very much encouraged to talk to us about it. I'm not going to talk any further about our self-paced, self-directed, target-based classroom. If that's something you're interested in, talk to us. Reminder, we said previously that according to Bernoulli, remember Marta's pronunciation from last week, according to Bernoulli's principle, we said our basic premise was that fast-moving air, oh goodness, I wish I had better handwriting. Fast-moving air has lower pressure, okay? So inversely, if we were to reverse that, if we were to say something like slow-moving air, we would have to switch this to higher pressure. And we, of course, recognized last week that this was achieved by blowing air into a vestibule here, and by having little sensors here, and little sensors here. They actually had them just on the exit of the narrow part, but I'm going to illustrate it here. So we had sensor 1, we had sensor 2, we had sensor 3. And of course, as this air passed through this space, it gets to here and accelerates. It speeds up. It goes faster because the cavity becomes narrower or smaller. So of course, sensor 2 out of the 3, this is the sensor which picks up faster air. Okay, faster air. But as it's effectively a baroreceptor, that faster air was detected at lower pressure. All right, and that of course means that sensor 3 and sensor 1, these ones here would have detected higher. They would have detected higher pressure. Why? Because the air in those parts of this journey is moving slower. Okay, so the air is slower here and here. So that means that the air is at higher pressure. Now, what does all this have to do with sport and performance? Why is this relevant? Why would we even want to consider Bernoulli's principle? Well, first things first, we're going to have a look at our javelin once again. And I'm actually going to chuck a term in down here that's going to be necessary for us immediately. This javelin is being presented with what we call an angle of attack. An angle of attack. So let me go back up to the javelin. The angle of attack means that it's presented roughly in this angle we have here, and generally speaking with the angle of attack we find that give or take it will be in the region of 45 degrees presented to the oncoming air. So we have an angle of attack of this javelin. In other words, it's presented at this angle, not steep, not flat, but at this angle. And anyone who's chucked a javelin a number of times knows that to get that angle right is not a straightforward thing. It's kind of a technical aspect of performance. So it's not just about having a strong shoulder, a strong arm, and a strong waist to flick the body weight through. It's actually a technical performance, right? So what do we want to do in terms of drawing on here? Well, first of all, we want to always draw our direction of movement, okay, our DOM. So we've got that in there, that's a given. But what we're interested to do now, and I'm just going to use this as an exemplification one, I'm going to show the actual technique of this a little bit more in a moment. We're going to effectively take two air molecules. So here's one, and here's two. Okay. Now, of course, we're gonna draw this. In fact, let me do that second one a little bit higher. And here's two. So we're going to draw this as if these air molecules are moving towards the javelin, but in reality, of course, it's the javelin moving through the air, right? So just be aware of that. So let's take air molecule one here. It's going to come to here, and it's going to pass under the javelin, something along those lines, okay? Something along those lines. So that airflow of that particular, let me do it in a different colour, of that particular piece of air has moved something along the lines of like that, okay? So the javelin's moved past it, and this air molecule has gone under the javelin, beneath, below the javelin. Let's look at the other one. Let's do it in some kind of shady blue. Not sure what that means. This molecule is going to come to here. Look, let's draw it in this way. It's going to come to here, and this molecule is going to end up going over the top of the javelin, and it's going to end up meeting the other air molecule somewhere back here. Okay, so we've had a different path or a different journey by these two pieces of air. We've had one underneath the javelin and one above the javelin. Okay, one underneath, the reddish one above the bluish one. So let's call this above. Let's call this above the javelin. Okay, and let's call this, what colour did I have? I think it was that. Let's call this below the javelin. And let's address what's happening above now. I've got too many blues as options here. Let's address what's happening above the javelin. Well, first of all, above the javelin is that the air molecule, this definitely isn't the right blue, I'm not going to bother. This air molecule is travelling further, okay? So would you agree with me that the path of that blue line is effectively longer than the path of the red line? So that means that for our below, we've got travelling less distance. So in total distance travelled, the one underneath goes less, the one above goes further. Okay. Next point, if the one above goes further, it must travel faster. Okay, so it's travelling further, therefore it must go faster, and therefore the one underneath is travelling less distance, so it's effectively travelling slower. Now, at this point, a student's going to say to you, well, why don't they just go at the same speed, and why does one suddenly go faster and the other one goes slower? And the answer to that is a good question. The answer to that is because, of course, the air molecules themselves are not moving at all. It's the javelin moving through them, and the javelin moves in one consistent set speed. It might be rotating around its axis, but it's moving in linear motion, all parts of the body moving in the same direction at the same time, at the same speed. So effectively, these air molecules have to get to this point at the same moment because the javelin's passing them. All the javelins passing at the same speed. So that's why. So as a result, what do we get? Above the javelin Bernoulli's principle, we've got faster moving air. Therefore, we've got lower pressure. Lower pressure. Okay, so above, we've got lower pressure. Below, we've got higher pressure. So, just to be clear, we now have a situation where we've got high pressure beneath the javelin, we've got low pressure above the javelin, and that creates for us what we'd call a pressure differential. A pressure differential. Now, the way that fluids work, gases and liquids, is that whenever there is a difference in pressure of the fluid within one fluid, if there is a pressure differential within the fluid must equalize that pressure. So of course what's going to happen therefore is there's going to be a force of air effectively recalibrating and resetting the air pressure by moving upwards, okay, by increasing pressure upwards. And what is that going to produce? Let me get my toolbar. That is going to produce, what am I doing? That is going to produce a lift force up. Okay, so we're going to end up with a lift force up. And of course that lift force, I've probably chosen the wrong colour there. That lift force is from the centre of mass of the javelin, which probably I should have put a bit more towards the tip, but the centre of mass of the javelin. So now we've got a lift force acting on that javelin, okay? So what is the overall impact of that? Well, as we know from previous studies, this is a reasonably heavy object. So this object should, in theory, move in a parabolic curve, something like that. But because we've got this lift force on this javelin, because it's been presented as an angle of attack, what we're going to get instead is we're going to get an extended flight path, and the javelin is going to land here rather than here because of the impact of that lift force. And it's for that reason that that angle of attack would be presented on this javelin. The only other thing I'm going to say at this point is about the concept of an aerofoil. Check spelling on this with students, please. Aerofoil, an aerofoil. And an aerofoil effectively is the same notion of it as an angle of attack. Basically, what an aerofoil suggests is that, if we were to look at a side portion of a wing, for example, okay, if we were to look at a side portion of a wing, for example, we'd find that a kind of an aeroplane wing would look a little bit like that, like an aerofoil shape. And of course, it's a bit more marginal in this example, but the air going above the wing has to travel further, and the air going below the wing doesn't have to travel as far. So that aerofoil again creates a pressure differential. And don't forget, on the back of the rear wing of a racing car, for example, they'd flip that aerofoil so that instead of having a lift force up, the aerofoil would be flipped to make it down force, and you'd have a Bernoulli lift force down force. And of course that's useful for cornering and turning at high speeds and maintaining grip, because you've got force down into the track. But that term aerofoil is really important to us, as is this one, pressure differential. Don't forget as well, you must add the term Bernoulli, in this case a Bernoulli lift force. Okay, Bernoulli lift force. And other points I would make onto here, I would also be saying things like extended horizontal flight. Okay, so we're basically saying the thing travels further as a result. Extended horizontal flight. We'd also be saying on there, for example, non-parabolic flight, okay, or asymmetrical, you can say, if you prefer that term, non-parabolic flight. So this is how we describe this scenario, okay? So we make sure we go through all the details of what's happening above, we make sure we go through all the details of saying what's happening below, and then we've got these other descriptive terms that allow us to express the movement of this. And one other thing that I just quickly address for you is, if we were looking at resultant forces, effectively what we'd have is we'd have our lift force up, we'd have our weight force down, okay, we'd have something like our weight force down, and of course what we'd have is we'd have our air resistance back, something like that. That's all of our forces acting on this javelin would be something along those lines. So of course, how do we go about managing that situation? Well, the first thing is we get a resultant force for the vertical forces. So if we add the pink vector, which is the lift force, to the green vector, which is the weight force, we end up with a resultant vertical force. So we'd actually end up with something like a small green force down, and we'd have that air resistance back. So again, we could then calculate our resultant force as we've done previously to effectively produce a resultant force on this object. Because first of all, we add this to this, and then we make the resultant force in this way. Now, in most questions, you're not going to be asked to go to that stage to produce a three-force resultant force. In this case, most cases you won't. But just in case you've got, your student's got a horror show of a question that got put in somewhere, that's how that's how they would go about doing it. Now, I've kind of already done the next job, because my next job was the idea was here to show all of the key language, the description. So I've kind of already done that, really, because I've said, look, we've got all the stuff above, we've got all the stuff below, we've mentioned our aerofoil, we've mentioned our angle of attack, We've said that as a result there's a pressure differential, therefore a Bernoulli lift force is created, and this is the impact of that. So that's effectively the language which would go into this description. So I'm not going to waste all of our time writing all of that out again, but that is the material which we'd expect to go into a description. And can I stress to you that if your students do get a question on this topic area, they must both draw and describe or explain, or whatever. They could evaluate, you know, or they could analyze. They could discuss, I guess. But they must, even if the question just asks them to describe, it's likely they're going to be asked for an airflow diagram, but encourage them to do both. Okay, so let's move this on. A couple of quick. I love this little activity on the left. So it's one of my absolute favourites. This activity here, WS7.2. Never get used to those codes. What does it ask the students to do? Remember, this is a worksheet for intuition. They could well simply only know about Bernoulli's funnel, high pressure, low speed, low pressure, high speed relationship. That might be all they know at this point. But it says here, this is a venturimeter and is used to illustrate Bernoulli's principle. Look carefully over the image and then answer the question below. Please note that this is not an exam style question. Explain why the water levels at point A and point B are different. And of course what we're looking for here is an explanation which is basically the same description as I've got here. Because what have we got here? Air is coming into the venturimeter here, and at this large opening, of course, this large opening, we've effectively got slow air. Okay, so we've got slow air and therefore we've got high pressure air. So that pressure pushes down on this water. Whereas here we've got a narrow opening, so now the air all of a sudden is faster. It's faster and it's low pressure. So now we've got low pressure acting down here. So of course the water effectively moves towards point A and equalizes that pressure. It's exactly that same relationship. There's a pressure differential. So they can use this language here, okay, not related to a javelin, to explain this concept, okay? So they can go about doing this. But this is where I think it gets fascinating. We've got a second activity here. Remember, someone said to me, oh, we don't want them spending too long doing this. Maybe there's an argument for that, but this really embeds the idea in their mind, okay? So do invest some time into these sorts of things. Venturimeters come in many different designs. Using the space below, please design an alternative shape for a venturimeter that would produce the same outcome. Now, I'm not going to give you an answer here because you could come up with almost anything. It's endless what could be achieved here, but we've got this model of a venturimeter here. We've got this model up here of how a fan would produce kind of differentials in pressure. And we're asking the student, can they effectively recreate one on their own? You could even go a stage further and get them to make it. Okay, so there's all kinds of, start bringing pipes in and water and fans, you know, do whatever you want to do. But that is a beautiful activity, really embed this idea of pressure differential. So I can't emphasize that enough. Secondly, we've got these paper experiments. Now, we looked at these rather embarrassingly last week. So I showed you the one where you blow across the top of the paper. Let me remind myself, I've got that one here, you know, blowing across the paper, which you saw me do in the session last time. But this one here is also a really nice one. You basically fold a piece of paper, make it stand like this, and the idea is that you blow through that gap. Okay, and what you tend to find, what you expect, or what the intuition of most people suggests, is that piece of paper will kind of open like that. But of course, what it does in reality is it closes, because you've got faster moving air inside the paper, which means low pressure. The air on the outside of the paper is not moving, so is at higher pressure. So of course it pushes the paper inwards. So it's a nice exemplification. And of course what you're looking to do here is you're looking for the student to take the key language that we've got here, pressure differential, Bernoulli force. Okay, they're not going to talk about flight, but they're going to talk about outside and inside the paper, the pressure differences and why they're different, the pressure differential. And that's going to, of course, get them using that key language, okay? And this one's exactly the same. This one's exactly the same principle. So I'm not going to go on about that in any greater detail. What I am going to do, and I've managed to miss off the end of my, look, if I go here, I missed the side of the page. I didn't mean to do that. But what I would do here, folks, just quickly, I kind of need to sit my drum, but let's get this one done quickly. What we've got here is we've got the same principle as the javelin with the discus, okay? This time the discus is traveling in that direction, so we've got direction of movement. Let's take two air molecules to begin with. I'll take this one. This one's going to go above the discus. And let's take this one, the greeny minty one. This one's going to go below the javelin, the discus, sorry. And the only thing I'd say in addition to this, folks, is that what you want to do is not just include one airflow arrow. You want to include multiple, okay? About 3 is ideal. And it can end up being a bit scruffy, not least when I do it. But you want to be looking at something like this, okay? What am I doing? Where's that minty colour gone? There you are. So we end up with about 3 airflow lines, something like this. Okay, so now we've got a full airflow diagram for your students, and we can see clearly that the air moving above the discus is travelling further. So again, we can go through exactly the same process. I'm going to go fast. Further, faster, speed, lower in terms of, let me put that in, lower pressure, above. Okay, so we've got further distance, faster speed, lower pressure. Below, we've got less distance. How would you say that in one word? Less, not the opposite of further, shorter, whatever. Less distance, faster. Sorry, what am I saying? Less distance. This is one of the problems with this topic. It kind of gets confusing in the mind, right? You have to get it you have to keep checking you've got it the right way round. Slower, and then of course higher pressure. What does that create? That creates the pressure differential. I'm just going to let's call it pressure differential. Pressure differential. And of course that pressure differential means effectively, we get that lift force up. Must label it L. You can label it manually as well. We get that lift force up, and as a result of that we get all of those impacts. So for example, we get pressure differential, we get extended flight horizontally, we get further distance, therefore better performance. We also want to be talking about that key language, angle of attack. Our discus is again being presented at an angle of attack. We can call it an aerofoil. Okay, again, we can use that same language to describe this process as a big crazy vehicle goes past my window, an aerofoil. And don't forget as well that we're talking about that extended, in fact, let me put it in there, non-parabolic flight. Okay, so we must address those points, non-parabolic. Now, ever so quick, and you can see here, folks, I mean, we've got a worksheet here that your students could really benefit from. The idea of this one is, of course, on the shot, the movement around is uniform. So no pressure differentials are created, assuming it's not spinning, more of which in a second. But on our other ones, including our rear wing, let me just show you the rear wing kind of example of this. We've got it here, look, let's, how do I do that? Let's take that. Have I made another one of those? Hey, look at that. I didn't even know how to do that. That's kind of exciting. Let's make it a little bit bigger. There's our rear wing. Imagine this is on the back. I'm really happy with myself. Imagine that's on the back of a racing car, rear wing. Okay, so the idea here is that this airflow molecule here has to go up and around the wing like this, and this airflow molecule has to go much less distance. Okay, so we've got exactly the same situation in reverse now. So above, sorry, I hope you were telling me off there for getting this badly wrong. How embarrassing. So this time we've got the airflow molecule going less distance across the top, and the airflow molecule underneath going further. Okay? Goodness me. The issues of doing things live, hey? So in this case, of course, this time underneath we've got further, underneath we've got faster, underneath we've got lower pressure. Okay, so lower pressure. And when we've got that situation, of course, and you can put all of the reverse stuff above, when we've got that situation, of course, we can say that there is what we call a lift force down. Okay, and I would term it that way because it's the correct term, lift force down. We do also use the term downforce. And why would a car do that? Why would a rear wing of a car do that? Or indeed, why would an airplane wing be manipulated to come in during the landing to do that? Well, it's because that that action of the air moving around the object in that way effectively applies pressure from above downwards because there's higher pressure above the wing. So on that basis, it pushes downwards. And on the racing car example, that means that when the racing car has to change direction at high speed, it's less likely that the wheels, the tyres, are going to slip off the track and end up in the gravel or the whatever, the wall or whatever. So here, if we've got a really bendy, turny track, something like the Monte Carlo Grand Prix in Formula One would be a good example, then of course what we tend to find is we get very big rear wings because you want a lot of downforce for turning tight turns at high speeds. And that is the opposite theory, of course, to these ideas. Okay, and will you be able to illustrate it here? Describe the speed of airflow around the object. Describe pressure above and below the object. Effect on lift. Okay, so we've already done that, so I'm not gonna go over that. And again, the javelin is exactly the same example as we've got previously. By the way, what did I get wrong here? I didn't put a direction of movement in, which we absolutely must do every single time. Okay, I need to change the canvas. I'll be straight back. Okay, time-wise, I think we're just about on track. We're maybe slightly behind where I'd want to be, but not a great deal. So let's move it on. Look, let's go straight on to looking at something a little bit different. Let's go on to look at what's called the Magnus force. But before we do this, I want to remind you, please, this is very important. I know you're going to go, James, you've told us 3 times already, but please be reminded, and please, when you get to this topic, remind your students that fast air moves or expresses low pressure. And remind your students that slow air expresses higher pressure. Okay, so make sure they grasp that concept is equally important in this type of example. We're going to look now at Magnus force. So think about Magnus force and Bernoulli to be based on the same idea, and that idea is this stuff here. Okay, so it's still based on that Bernoulli principle. But there is a difference. What we've looked at so far, whether it be the discus, whether it be the javelin. By the way, a ski jumper is great as they fly through the air. If you let me just sketch one on a ski jumper who would be something, they kind of make this kind of shape, don't they? That would be a great example of an aerofoil, okay, with a ski jumper, because of course the air below goes whoop like that, and the air above goes whoop like that. So the air above has to travel a lot further. So don't forget ski jumper. I don't know if they're going to get that question in the exam, but it could. The principle is identical. Anyway, what we're doing here is a different thing. We're going to look at Magnus forces. Now, let me remind you what this means, this type of resource. This is what we call a note sheet. This sheet is supposed to be used when they take a video tutorial by us, in this case on Magnus forces. Okay, so that's what this is for. They take a self-paced tutorial by us, take the teaching by us, and that of course potentially frees up more time. Now this object here, this is the tennis ball, of course. I'm going to assume that this tennis ball here is moving with top spin, and I'm also going to assume that it's moving in that direction. Okay, so we've got direction of movement that way, but it's moving with topspin. So I'd immediately encourage you to think, right, what way is this ball turning? What type of rotation around its transverse axis is occurring? And of course, that type of rotation would be in this direction, or clockwise direction. Can we all agree with that? That would be the direction of a topspin. You know, the ball's been hit with an eccentric force off the centre of mass. Remember, we talked about that. And of course, it's meant that the ball effectively starts to spin around its axis, its transverse axis in this case. So that's all well and good, fine, the ball's spinning, but this is the crucial part. This ball is not smooth. Even if we were talking about a golf ball or a table tennis ball, which kind of feels roughly smooth, it's not smooth. If we look at it under anything like a microscopic level, it's incredibly rough. Equally, this surface here, we know it's rough because it's kind of bobbly and fluffy. It's a tennis ball. So as this ball rotates, it also rotates. Now, I'm only illustrating this concept. It also rotates and picks up molecules of air. Okay, remember that air is a mixture of gases. I'm just going to talk here about air in general. But it's picking up molecules of air. And as a result, this air is also spinning. It's spinning with the ball, attached to the ball. And we call this concept the boundary layer. Boundary layer. I hate the word boundary. I always feel like there shouldn't be that A there, but I'm guaranteed that there it is. The boundary layer. Boundary. Close to insanity some moments. Anyway, let's move on. boundary layer. Why have I said it again? Right, what am I doing? Okay, so as a result of that, this boundary layer is spinning with the ball. It's spinning in a clockwise direction. Meanwhile, we have air, which is coming here and here, exactly as we've talked about before. So this air molecule travels around this tennis ball, completely uniform to this one. Can we all agree with that? So we've effectively got the same distance above and below. So no pressure differential, James. No pressure. Well, actually, that's not quite true, because of course what we find here is that in reality, if we look at, say, this little piece of air here, it's traveling in that direction, whereas let's say this one here is traveling in this direction. So at the bottom of the ball, the boundary layer is traveling with the airflow. Above the ball, the boundary layer is traveling against the airflow. Can we see that here? Here, this boundary layer is traveling like that, and the airflow is traveling like that. Here, this boundary layer is traveling in the same direction as the airflow. So what does this mean? Well, it means at the bottom of the ball, get ready for this, we get fast, or sometimes what we call smooth flow. If you are familiar with the word laminar, you would be very much encouraged to use that here. Smooth flow or fast flow. That means that under the ball, we've got low pressure. That means that above the ball, here, we've got slower flow. You know, effectively the boundary layer is hitting the oncoming air. Slower. We could also call it turbulent, by the way. We've got slower, and therefore we've got higher pressure. And that's because the boundary layer is hitting the oncoming air. Okay, and what does that create as a total? Well, if I just put my toolbar open again, that creates a Magnus force down. Okay, we get a Magnus force down. Now, if we go back to the concept of topspin, why is this useful? Why would the Magnus force down be useful? And of course, it becomes part of the, if we think about it in the tennis context, it becomes part of the science of how to apply the technique of tennis. Okay, a couple of things. The flight of topspin is higher over the net, so the flight is higher. Okay, so the ball is less likely to hit the net. So higher over the net. Secondly, the ball dips in its flight. Okay, so at the end of its flight, the ball dips down. Why? Because there's a Magnus force acting down. So we've got what we call a shortened flight path. We've got a shortened flight path. And why is that useful in tennis? Because the ball stays in. Okay, so we use topspin to control the ball and to bring it down and land it within the baseline, say, or I guess it could be another part of the court, but the ball stays hit in. So we can hit hard and keep it in. So therefore, topspin becomes what we call an attacking shot. And I'm going to talk about the bounce of the ball in a second. Okay, so we can play it as an attacking shot because we can hit the ball hard, but the ball is going to dip in its flight. Just to remind you of that, the flight of this should be like something like, I didn't do that. The flight of this should be something like that. Actually, didn't do that very symmetrically, but the flight of this actually ends up being something like that. Okay, not quite as dramatic, I think, as I've shown it. It doesn't kind of come down quite as vertically as that. That's a bit more shuttlecock-like. But you get the idea. It shortens its flight path and keeps the ball in. And that's why that topspin is so effective. If we look at the same principle now for backspin, let's say we're going in the same direction again. We've got a direction of movement in that direction. This time, the ball is spinning in this direction, anti-clockwise. So, of course, the air molecules are also spinning in that direction. Put a couple more on there. Are also spinning in that direction. So this time we've got the oncoming air going above. We've got the oncoming air going below, traveling the same distance. So which is a uniform object, we would think there's no pressure differential. But of course, in this situation here, this air molecule here is traveling in that direction. Sorry, this boundary layer, whereas this one here is traveling in this direction. We get a collision. So here we've got slower air, And here we've got higher pressure. Here we've got higher pressure. Okay, so we've got slower air, we've got higher pressure, as opposed to above the ball where we've got faster air, because this molecule here is traveling with the airflow. I'm doing this really scruffily, going with the airflow. So we've got faster air, we've got lower pressure. I'm just mocking myself for the quality of these images. Lower pressure, and of course, what does that mean? It means that we have let me choose a nice colour for this. We have a Magnus force up. Okay, so we have a Magnus force up. And what does that mean? So that Magnus force, it means it travels low over the net. Goodness me. Travels low. What is that? Low over the net. It also means that the flight is extended flight, because of course the ball effectively hovers a little bit in the air, I guess you could say. Extended flight. We've got the ball goes deep in the court. Okay. And it's hit slowly. And why is hitting the ball slowly in this case useful? Well, it could be for two reasons. One is just shot variation. You know, your opponent experiencing different types of shot. But the other one is to recover position. Okay, so we use a backspin in table tennis, often in tennis, for example, when we're looking to recover the position. It would also be used in something like golf, of course, to as I'll talk about this in a second, to lengthen the flight, but also to grip when it lands, and I'll talk about that in a moment. So this is what we call a defensive shot. Defensive shot. This backspin shot. So we can see how these Magnus forces can be utilized to really good effect within something like a tennis or a table tennis performance. Now, we've also included ones here. So these ones would be exactly the same here. You get the idea. We've got the tennis ball. We've got the two tables tennis balls, exactly what we've just talked about. But don't forget as well, this could be to do with side spin. You know, in this example on the right, if this is a right-handed player, then if the ball is traveling with that spin, this is going to create a slice effect. And ultimately, rather than the ball dipping down, the ball is going to deviate to the right in this case. Whereas in this example, if the ball's been played with kind of a, what do you call it, a hook, in this case the ball is going to deviate to the left. Now, often in golf we want to avoid these situations and hit the ball straight, but if the hole is not a straight line, you have to go around a corner or bend, or you're trying to miss a tree or whatever, then of course these techniques can be very, very useful, and this Magnus principle can be really, really neat in this situation. So just be clear, so when the ball spins, in this case this would be on its longitudinal axis. We're looking at the ball from above here, just to be clear on that. We're looking at the ball of these two here from above. The ball is spinning around its longitudinal axis, more of axis next time, and it's deviating to the right for the right-hander for the slice, and it's deviating to the left for the right-hander for the hook. Okay, so we'd call this a hook or a draw. We call this a slice, and we can also call it a fade. Okay, a slice or a fade. And they're nice techniques to be able to produce, because it means that you can, in the golfing situation, you can manipulate different circumstances to a positive end by using this exact same principle that we talked about here with the boundary layer of the ball. And again, the other thing is, think about the surface of the ball. The surface of the ball is literally designed to carry air in it. Those little pockets, those little dimples. Is that what they call them in golf? I'm not a golfer. I'm terrified of going to, if I ever get invited to a golf club, going to, like, you know, one of these, like, my dad goes to a really nice golf club, and he sometimes gets me to go and pick him up because he's had 3 shandies or whatever, and I pop in to say hello or whatever. I'm never more out of my depth comfort zone than I am in a golf club. But anyway, that's another point. But these balls are designed with these dimples to actually produce this effect. You know, I guess most typically is for backspin, is for the 2 side spins we've just talked about. You could look at this side spin as well. You could look at this in relation to something like a swerve or curl of something like a football or a rugby ball, that sort of thing. Okay, so swerve and curl would, so people often talk about Ronaldo free kicks or stuff like that. But I would just say on the side spin of footballs, the thing that's interesting with a golf ball is that its shape remains relatively constant during its flight. So in golf, the ball remains pretty round during its flight. On the moment of contact, it does squash down. but afterwards it's pretty round during its flight, so it's pretty uniform shape. A football, however, is really compressed at the moment of strike, and that compression of the air through the strike can actually influence the dynamics of the ball. So while it looks round to the eye, there's all kinds of internal motion of the air going on, which actually changes the way the ball flies. But if we just take the basic principle that the ball is spinning on its axis, spinning on its longitudinal axis, of course side spin, swerve or curl will be produced because of Magnus force left or Magnus force right. So it's a really nice thing to do. Okay, we've got one thing to do, which is to answer a question. I'm just going to take a briefest pause just to sip my drink. Cool, I've just been handed what may be the greatest cup of coffee known to man. Beautiful. Let's have a look at this question. Explain how a javelin thrower achieves maximal horizontal distance travelled. Make reference to Newton's laws and fluid dynamics in your answer and use vector and airflow diagrams to illustrate your answer. So I would say that in terms of Bernoulli principle, this is as challenging as it's going to get. And therefore we're looking at the toughest level of questioning here. I would only add that obviously if we were looking at a Magnus force example, we'd have to incorporate that boundary layer and spin into the equation. Let's have a go at this. So the first things I want to address is I'm explaining, what am I doing? I'm explaining how, okay? So it's important that I'm explaining how. When we explain how, we use things like because, we use things like through, we use things like by, we use words like this means, we use terms like therefore, comma. Okay, this is the kind of language we're going to be using to explain how something happens, and you should be expecting your students to do that. Please consider our roadmap solution to help them do that because it works. It's a beautiful thing. Anyway, enough sales. Let's move on. Let's have a look at the first part of this answer, which I did in advance. Okay, so let me start answering it. I realise some of you are just going to sort of take this in now and maybe write it down later. We are also going to give you model answers for these at the end of the course. Okay, so for all of the questions we've done, you're going to get model answers. So don't feel like you have to scribble down everything on this particular point. You might just want to take down themes and key ideas. Increased distance is achieved by, there's our kind of explaining how language, by throwing with an angle of attack. Now, if I had the first canvas on, we could go back and look at where angle of attack is a key term. We've got to use it. This means, I'm explaining how again, an angle of 45 degrees and produces an aerofoil. Okay, so I'm clearly explaining, I'm clearly introducing the idea of how extended flight can happen with a javelin. I've got my green correct answers in there. I've got my orange, just in our demonstration purposes, of course. I've got my orange key connectives there showing that I'm explaining. It's a beautiful start to an answer. But of course, we've got to take this a little bit further. Let's move on. We've been asked to do vectors and airflow diagrams to illustrate. Illustrating is like explaining. It's a skill that a student should be able to perform. Now, I made a decision just to do it freehand and to do it with just the black color so you can see what it would look like on the exam, okay? So what the student might produce. So it would look like this. Notice what we've got here. I'm just going to give little ticks. We've got a direction of movement arrow. We've got airflow. We've got airflow below and above. We've got a lift force up, which has been illustrated from the center of mass. We've got an angle of attack. We've got clearly showing that the air above is traveling further than the air below, and so on and so on. That illustration does a great job for us, but we've got to explain it. So let's go through the explanation. Air traveling above the javelin travels further. We could kind of, I think in this 50 mark, it's not going to be it's going to be a leveled answer rather than a circle, tick, one mark. But look, these things are getting circles and ticks, right? Circles and ticks. If it was a 4-mark question, it would be circle, tick, 1 mark for each. Circle for further. Therefore, comma, look, therefore, comma, that comma, for goodness sake, expect them to use it. That their grammar should be right by the time they're 18. When I was 18, mine wasn't, because we didn't do this stuff at school. My grammar's way better now because I basically taught myself how to do it, and Marta, who's sitting with me tonight, points her finger at me every time I get it wrong. But students need that opportunity to develop their grammatical expression. So let's help them with that. Therefore, comma, it travels faster. So the air over the top goes further, faster, which according to Bernoulli, look, we'll mention him there, means it has a lower, that's meant to say low, it has a lower air pressure. Below the javelin, now we do the other side. Below has less distance to travel. it's slower, and therefore it's at higher pressure. Okay, so I've explained now, or I guess it's more of a description in some ways, but I'm explaining what's happening below and above the javelin now, and I've got the illustration to support the answer. Let's move it on. This means, there we go, we've got our language from above. I'm still explaining. This means a pressure differential is created, circle tick, and as fluids always move from high to low pressure. I mean, I could get that. Again, can I just note to you, comma, where's my little comma there? It's there, look, comma, and there is created, and as fluids always move from high to low pressure, comma, a Bernoulli lift force is created. Okay, so there we go. And then we've got according to Newton's laws. Remember, we had Newton up here. According to Newton's laws, according to Newton's law of acceleration, so again we've got law of acceleration, acceleration of a body is proportionate to force acting. Okay, so I'm using Newton's second law to explain how this is working. This means the javelin deviates from its parabolic path and becomes non-parabolic. I think that really should have been done in green there, just so you know, non-parabolic. Not too sure, I'll probably just confuse myself. Non-parabolic, okay. And horizontal distance is extended. Now, I've kind of got a foundation of a really good answer here, but I want to take it a little bit further. I want to draw a little bit more. I've got a little bit more to offer. So here I'm giving a little, again, just freehand, so it's a little bit scruffy because it's like a real exam. So I've got no Bernoulli as my flat line, Bernoulli is my dashed line, increased distance on the horizontal distance covered. The parabolic flight is in a state of inertia. Again, the parabolic, there's no forces acting during the flight, or the weight force is dominant, so it remains parabolic, it's in a state of inertia, or following the law of conservation of momentum. Okay, so I've explained now why the forces acting would make a big difference, and then I ran out of space at that point. Now, a couple of additional things that I would throw into this answer, just in case. First of all, I'd take my javelin, and I'd put my weight force on, I'd put my air resistance on, and I'd put my lift force on. Okay, so I'd put those three forces acting, and then what I would do is I would take that a stage further if I was the student here, and I would say that results in a small downforce and a force like that on the javelin, and then what I would do is I would put my resultant force in here. Okay, and we could say the air resistance is dominant. This creates, this causes a deviation in the flight path and extends the flight path and so on. So I would be putting those in there as my vector illustrations. But I suspect in this answer it's probably above what's required. But anyway, I would still be putting those. I would still be putting those things in there. So that would be how we'd expect a student to go about answering a question like that. And one of the things you might know about biomechanics is even if it's an extended answer, it's a 15 marker on, I think it's 15 marks on OCR A level, for example, you often find that the answers are very concise. You get your points in, you draw, you're done. Okay. In this case, we're explaining, so we shouldn't really need to make a conclusion. Maybe we would make a conclusion, perhaps, but it's not necessarily a requirement of an explaining skill. But here, obviously, we've got a nice, concise answer which gets us there. Last thing for today, I was going to talk, well, I will quickly mention that, but last thing for today, I just want to mention spinning balls and bouncing. So I want you to imagine this is a ball, and it's travelling in this direction, but it's travelling, as you can see there, with topspin. So it's going to come in, let me get my toolbar back. I meant to mention this before, by the way, sorry, I forgot. So it's going to come in, it's going to hit the ground at a relatively steep angle, because it's topspin, it's dipping down its flight. And what I want you to realise is the ball's going to be here on the ground. The ball's going to be here on the ground, and it's spinning in this direction. It's top spinning. So what does that mean? It means it creates a friction force. If imagine if the ball is likely to slip, it would slip in that direction. So it's creating a friction force forward on the ground. So as a result of that, when the ball leaves the ground, it leaves it pushes the angle back like that, so the ball kicks off the ground and goes further and pushes back. If we imagine a ball which is doing exactly the same thing, let's take a red ball, sorry, let me do that again. Let's take a red ball, and this time it's traveling with backspin. Okay, this time it's traveling with backspin as it comes into the ground. Okay, as it comes into the ground here, this time this backspin is going to be spinning in this, is going to be spinning in this direction. Okay, so this time, this ball, what it's going to do is it's going to sit up in its bounce. It's going to sit up in its bounce, and it's going to end up here in this sort of very hittable position. So I just wanted to stress that there is an impact of spin on bounce. I meant to mention it earlier, but I just forgot. Finally, we have this experiment here. If I have got time, I'll quickly show you it when we come back on the screen. But it's a cool one. It might take your students a little while to do this, but it's a really great way. If you take the Magnus effect, you can literally produce it using cups, elastics, and and a bit of sticky tape, really. So yeah, I'm not going to go over the whole thing, but it's in your pack. I encourage you to have a go at it. The students will absolutely adore this, and it literally exemplifies the Magnus effect there and then in the classroom. Why? Because when they release this thing, as they pull it and they release back, of course, the cups are spinning. Okay, and whichever way they're spinning, it's either going to deviate down towards the floor very sharply like a top spin, or it's kind of going to float upwards, really exaggerated. It will literally float up towards the ceiling like a backspin. Now, of course, the backspin of a tennis ball is not going to float up towards the ceiling because it's a heavier object, but these really light cups will. It'll literally float off. It comes down eventually, but it literally floats off. So I really encourage you to do this, possibly even do this as a first access experience to something like Magnus Force if you're studying that. It's a beautiful activity. Get your students stuck into it, get them covered in tape and elastic, and get them figuring out. What you'll find is if you've got 5 or 7 pairs or 10 pairs doing it, 3 of their little models will fail, and about 30% will fail, and about 70% will be successful. That's what I found in the past doing this sort of thing. So it's kind of a nice one because it also tests them about actually following instructions from the sheet as well. But basically, as you see here, they get 2 cups, they tape them together here, and they make an elastic which becomes like a catapult, really. And as they release the elastic, this thing effectively flies off. But as it's flying off, it's spinning really hard, and that spinning produces the boundary layer, and that boundary layer produces the Magnus Force. Right, enough of me babbling. I have kind of ruined the end of this show by not making myself clear enough. Let's go back on the camera.
Okay, we're on.
Yep.
We're good. Yeah.
Mm-hmm.
Okay.
Yes.
Ah.
Yeah. So yeah, we just wanted to apologise. We noticed there were a couple of mistakes on the note sheets. We missed a bit when we added them while the session was ongoing. But we do apologise. We realised there were in the note sheets there were a few mistakes.
Mistakes or things missing?
Things missing. Yes.
Okay. Are they in there now?
Yes, they are in there now. Yes.
Okay. Well, apologies to everyone for that. Yeah. Well, they're in there now. That's good. Yeah, that shouldn't happen. Yeah, I apologise for that. Okay. Yeah. Anyway, let's take questions. You got any first of all?
I don't. I think this this session was very clear. Well, last week I wasn't quite sure about the whole Bernoulli theory and stuff, and I did understand it in the end. I thought this session was very, very clear.
Okay, we've got a question actually here from Ryan. I'm going to take it straight from the screen here. So Ryan very kindly asked a question. Thank you. And by the way, Martin, I don't know if you want to keep an eye on the phone for any checks there, which is because I sort of forgot about that bit. I don't think there are any, but have a little look. Ryan's question was: you explained how topspin reacts when it hits the ground. Can you explain why, when the backspin shot hits the ground, it bounces up and not forwards, please? Yes. So the core to that principle is that friction is the anti-slipping force. So if the ground is here, and the ball is coming into land and it's backspinning, it's spinning that way. Okay. So its tendency to slip is forward. So therefore, the friction is going to act backwards from where the ball has come from. So the ball is coming in from here, back spinning. It grips the anti-slipping force is that way, and therefore it pulls it back in the direction that it's come from, and it sits up rather than bouncing forward. The topspin does the exact opposite of that. As it comes in, okay, its tendency is to slip that way. So it's thank you. So it's the backspin is spinning this way as it hits. Its tendency is to slip that way, So the anti-slipping force, the friction, grips it that way, and of course then it means it sits up more. The topspin, it would slip that way, so the anti-slipping force is that way, so it kicks on, which is why the topspin in table tennis and tennis is the perfect attacking shot, because not only can you hit it hard and it will still land in court or on table or whatever the equivalent is, but also it will push the opponent further back in the court, which is why if we look at someone like Nadal, for example, at Roland Garros, he'll use very heavy topspin, push his opponents very deep in the court, and then employ things like drop shots. To be fair, Nadal doesn't use that many drop shots. He just tends to power it past people. But theoretically, you push the opponent back. They've then got literally more time with the ball in the air when they hit the shot. It allows you to maneuver yourself into position to, with more time, and then you can keep the opponent back, which is why getting into the attacking position in things like tennis and table tennis is so important, and pivotal and central to that is the role of topspin. Backspin's more of a defensive recovery shot, but then we look at people like Murray, for example. He tends to use it for the change-up. It's part, in some ways, of his attacking arsenal. Also, the biting, standing-up ball is useful if you do something like a backspin drop shot, for example, which is why you'll see it employed a lot in table tennis. You'll see it employed a lot in tennis as well, to make the ball sit up and work that way. I don't know if that makes sense or not. Ryan, it does. Thank you. That makes sense now. It's a pleasure. I obviously didn't do it very well first time. Tim Brown, don't worry. I'm assuming that's about the notes. Yes. Look, I mean, my view, I really appreciate your kind words. My view is we should get it right. So we should get it right. So yeah, we will obviously learn from that, and we'll get it right. Any other questions, Marta?
No, I haven't got any more. And at the moment, we haven't got any text. But of course, if you haven't got any questions,
from my mum.
Not even from me. I've got one from EE, but I don't think they're going to ask anything about biomechanics.
I am going to address one other point, which I very, very nearly put in the show today, but I didn't put it in the show because I don't think it's going to come up on any A-level exams in our subject, so I felt it would be sort of 10 minutes not used that well. And also because it kind of takes in a different direction. But what the point I wanted to make was, it was the role of swing in cricket, for example, the swing of the ball in cricket. And I'm going to simply pose a question here tonight, and I'll address it next week. Why would we find, for example, that a ball that is presented shiny on one side, smooth on one side, and rough and sort of jagged on the other side, and why the ball is also presented in a way so that the seam operates, it's often at around about 70-degree level on the ball? Why would that cause deviations in the flight? So I'm just going to pose that question, and we'll actually answer that question, because it's a really fascinating thing. And then we can attempt to address the notion of reverse swing, which I believe has been better explained now, but still is a relative mystery. But for conventional swing, can colleagues take the points we've made tonight and relate them to that kind of principle? Can they look at smooth side and rough side, and also the angle of the seam, creating greater distance on one side? And can they figure that out? And it's just a little challenge. It's not going to probably make any exam difference, but I thought I'd chuck it in there. So, Michael, when striking a golf ball, it drastically changes shape. So does that have no significant bearing on the airflow travelling further on one part of the ball? That was the point I tried to make in the demonstration. I don't know if I didn't make it well enough, but basically, if we look at the golf ball, you're absolutely right. It drastically compresses at the point of contact, Michael. But once the ball then is in the air, let's say 10 meters away from the club head, or flying off into the straight down the fairway. I'm sure your shots are, mine aren't generally that good. But once it's released from the club head, it effectively turns back to its spherical uniform shape. Whereas what's happened, because it's a much more solid object, whereas the football, effectively the innards of the ball are still moving around inside the ball. It's a much more mobile and dynamic environment inside the ball, so we can't judge it as specifically. Whereas in the sense of the golf ball, once it returns to its uniform shot, which is, I wouldn't want to put a distance on it, but some meters after it's been hit, then of course the airflow works in exactly the same way. And of course in golf, golfers will use backspin, very rarely use topspin, only if they're really in trouble and it's a specific shot to get out of a very odd scenario. But golfers will use backspin for two purposes. One is because it extends the flight of the ball. to take it slightly further. But more importantly is the point that Ryan asked about, is the biting impact of the bounce, so that they can basically, I think they call it attacking the pin. They can attack the pin, bounce the ball very, very close to the hole, and be confident that it's not going to kick on and run off the back of the green area, for example. So that would be why. But to answer Michael's question, the main point is that the ball returns to its uniform nature quickly after it's become a projectile. Not immediately, it's going to be some meters, but once it's in the air, it basically returns to its uniform shape. So yeah, good question, actually. And I just want to, one other thing on golf balls, it took, I'm not a golfer, so I always struggle a little bit with these terms, so maybe someone even wants to correct me. But of course, just one thing on axes, if we look at something like top spin and backspin of a table tennis ball, where did my ball go? If we're looking at top spin or backspin of a table tennis ball, then this is rotating around the axis through its side. We call that the transverse axis. Well, on most exam boards, we call it the transverse axis. Don't get me started on that. But it's the side to side, which, correct me if I'm wrong, Marta, absolutely should be the transverse axis, right?
Yeah.
Side to side.
So, yeah.
So that's rotating around that axis. When, of course, we're talking about side spin of the ball, for the right-hander, for example, that would be a hook or a draw. This way here would be a slice or a fade. We're talking about rotation around the longitudinal axis, or sometimes we call it the vertical axis. Okay, so just be aware they're two different axes of rotation, even though the principle works in exactly the same way. Michael, okay, I get it. Really well presented, even. Thank you. Well, Michael, thank you for that. I appreciate the comment, because we're going to go for a lovely curry after this, Martin. I'm going to be a bit like that, frustrated that we cocked up. Those things annoy me deeply. So I very much appreciate you saying that. And yeah, I mean, for me personally, I'm really fascinated by this topic. There's little things that kind of bug me about the topic, though. Like, I'll give you one, and you might find this. I wouldn't necessarily encourage you to do this with your students, because it will frustrate them a little bit. But if you go and sort of deeply research the principle of the Bernoulli principle, for example, and you go on sort of some progressive Google search and look at some more deep level papers on this, you're going to find that a lot of the principles we've just talked about are questioned at the sort of levels above this. We've all experienced that, where you learn at a GC, then you learn at an A level, then you learn at a degree, and they tell you slightly different things, right? And it's the same with this topic. So I just throw that caveat in, because a lot of people argue that, for example, the Bernoulli principle applied to an aeroplane wing, which of course is aerofoil shaped, is nowhere near the most significant factor which causes the rise of that plane. I've read things where it's 2% in comparison of the thrust of the engine generating the lift. So just be aware of things like that, because there are little caveats, and you may find the students come back to you and say, I read this thing that said, just be aware of it, that these are ultimately principles and theories which can be challenged of exactly how they work and how they operate. We don't need to worry about it at all in terms of teaching a GCSE or an A level. This is more than enough that they need, but just be aware that those other arguments are out there. Other questions, Marta? Anything on Twitter? I see we've got a couple of notifications, so I'll be very quick. Very nice very nice tweet here from Luffer PE, which I believe is Tim down at Bishop Luffer, which is really kind. Another session. Thanks, James and Martha. So Tim, if you get to know Martha well, you realise that
welcome, Tim.
that's the anglicised version of Marta. How do you say? Even though we've known each other 15 years, how exactly do you say your name, Marta?
Marta.
Yes, I'm not going to do it. I actually speak Marta's language, but it's a simple word, but I can't quite get it. So look, let's start to wrap things up. We'll just check for any more questions, see if we're not missing anything.
Nothing on text. People need to get on texting and ringing, and having real people talking to us.
Yeah, well, I think it partly comes from numbers. I mean, we've got 50 schools who are involved with this project with the Biomechanics. We've got about a third of those schools that take the session lives, and 2/3 that take it on demand because they do it at school together in their teams, which is absolutely understandable. The other thing, I don't know how people feel about it. We did a CPD show last night, and we were saying to people, if Tim, Michael, Helen Philpott, who I've been chatting to tonight, although she's not on the show tonight, for example, because she had childcare considerations this evening. If you guys actually want to come on the show and come and talk to us, I mean, we do some work directly with Bishop Luffer down in Chichester with Tim, for example. We'd like to get you in the studio. I don't know. Can we quickly show how it works, Marta? Well, that camera's right on the edge here. Do you want to just show quickly how they're? I mean, there's a bit of a mess, but do you want to just quickly show them how it's set up?
Big mess. Currently we've got a camera that's not working. That's why I'm not on screen either. Well, I'm quite happy about it, but right. So here's James. Here's the computer. The camera
also
that's not
James.
working.
Yeah.
That's also James. Yeah. That's going to be a bit of a. There's the window.
And Marta, the other thing, can you just show the mixing deck? I think it just turn it around.
Hold on.
It's going to make a mess. So basically, folks, we have the capacity in this studio to do, even though it might not seem like it sometimes, we have the capacity to do relatively professional TV productions in here. And we'd really value people coming on and either speaking to us via Skype or something like that, or coming on and actually coming into the office if you're near enough and come and being part of a project with us. So if you've got something that you want to share, I said last night to people, it doesn't need to be anything elevated. It could be like a brilliant way of organising a store cupboard. Come and talk to us. Let's elevate the conversation. Let's share it with people, and let's go from there. Okay, so
to be fair, if it's about organising a store cupboard, we could really do with
we could
good
do
advice,
that.
to be honest.
Couple of points that's on there. Michael's made some really nice point there. Don't be offended, but so much better than I anticipated. Brilliant. That's really kind of you, Michael. Thank you, my friend. Tim Brown, there's a good clip from Magnus Effect on YouTube where a basketball is thrown off a dam. I'm not allowed to put the link on here. Oh, okay. So, I mean, I guess if you search YouTube, go basketball dam Magnus Effect, you're going to get a good chance. By the way, that practical with the cups and the elastic bands, I can't recommend that highly enough. It emphasises Magnus beautifully, so I really recommend you do that. It could be a great introductory topic. That could just be a cool thing to do with your registration, with your tutorial group, like a little science experiment with cups. No, I mean, that's the sort of stuff that I used to do. But anyway, maybe that makes me odd. Anyway, we need to sign off. Marta, you and I have got a curry to go to. And these people have got lives to lead. So yeah.
I think we may have one last text.
Oh, one second. We do understand if people need to go, but we got a bit excited, so we're going to stay on. What's the text?
Right, the text says, hold on. It says, sprinter accelerating off the blocks. Calculate the sprinter's mass from session 2. Any chance of a revisit? Craig from St. Mary's.
Yeah.
He also says self-paced learning is taking off. Absolutely loving the journey. Thank you very much.
Amazing. Well, Craig's a bit of a hero. He's a bit of a legend. He works, got to know Craig a little bit in recent weeks and months. I'm more than happy to demonstrate that. No problem at all, or to go over that again. I'm just going to say that let's hold it back for session 6. So I suggest we just do that because of time and because of my little rumbly tummy, and we've got kids to go and meet for dinner, so let's do it that way. But Craig, absolutely, we'll make sure that gets included in the session next week. If you want to address it before then, you and I can speak about it on the phone and go over it, and yeah. So if that's okay with people, so yeah, let's sign off, Marta. I'll stop the stream on YouTube.
Brilliant.
And just wish everyone a very good evening. Thanks again, and apologies for the notes that won't be happening again. Put it that way. Thanks, folks.
Thank you.